So this particular question number 25. This particular question number 25. Like few others of this chapter are solved incorrectly by many people. They have published the wrong answers. Just unacceptable. It's misleading. So I'd solve this question in two different ways. One, in the wrong way. Actually, there is a subset of the wrong ways too. There's a wrong way and there's a right way. There are two subsets of a wrong way. All right. Uh, so solve both both of them, and of course the right answer. So the question is that there is a cylinder, and in this cylinder we kept an ice block. I'll try to make it 3D so it's better to understand. There's an ice block, and with time the water melts from this ice cube. It's uniform from all the sides, so all the sides. It's just an assumption. Otherwise, the bottom part melts the fastest. But anyways, it's just an assumption that the all the sides melt uniformly, and so the length of the side decreases by the same amount of all of them in the same amount of time. So what's the time duration when this ice cube will leave the contact with water? Now let's dig deeper into the image. Let's get a better side view. This is our ice cube. Now it's melting. So let me. This is the water. This is the water. So it's melting, and of course, immediately it will not lose contact at 0.001 second because it's heavy, and the water, this water of dx thickness, will not be able to pull it up. We need a water of some thickness so that it causes a buoyant force and so it leaves contact. So let's assume that the water, what of water we want is of height h. It leaves contact. We are just talking about the time it leaves contact. Okay. So this is height h. Let's say it's leave contact, but this small thickness can be approximated to zero. It's just the point. It's left contact. So just you know that's how I'm doing the diagram. Just left. Yeah. Similarly, here, focusing too much on diagrams actually. So this is how you see it. Let me write all the values. So this is the radius r that's given, and we've been given the edge. We're not given the density of ice actually. So we do not need this question. So first I'll solve it the right way, then I'll solve it the wrong way. So for it to lose contact, just to lose contact, just the point it loses contact, it should be in equilibrium at just the point it loses contact, and the buoyant force must be just slightly greater than the mass. And since it loses contact, there is no normal force. There is no normal force since it loses contact. It's just the buoyant force that keeping it up, keeping it at equilibrium. And after some dt time, when it will melt a little bit more, the buoyant force will be, because it will cover a much larger volume, it will be more than its mass, mg, weight, and so it will move up. The ice cube will move up. Now, like in the equilibrium conditions, mg should be equal to, okay, now is equal to the volume inside. Okay, we do not know what volume is inside, so this is the volume inside. Let me mark it with red. So this volume is inside. Let me say the volume is v, so it's v times density of water and of course g. So m is equal to v 10 to the power 3. Now m is also given. Now the total volume of this whole ice cube, let me assume it's vt, right? It's vt, the whole volume. So vt times the density of ice, it's not given, but I'll just try it. 9, it's not given, and we do not need this to solve the question actually. So volume total, acha. And also volume, what is this equal to? It's equal to the base times area. The base is, let's assume originally originally was a bit larger, like this. And originally the length was a, right? So length was originally a. Now we have assumed it's e, but I'll rather say it's b, right? So the volume total is height, sorry, it's b cube, since it's a cube, 0.9. The volume inside. The volume inside this red area, how much is this? It's the base, which is b square, times the height, h. So get b 0.9 times 0.9 is equal to h. This is our first equation. Now we cannot, now here's the thing where people go wrong. We cannot find h here by volume conservation. People do, but it's wrong. I'll tell you why later. Now, the simple phenomena of mass conservation. It says the mass, of course, is unless and until it's not converted to energy, it's conserved. And I do not see any kind of nuclear reaction here. So, by conservation of mass, originally the mass was AQ volume, density 0.9. It was the original mass. Final mass is the mass of ice, which is BQ times 0.9 plus this mass of this water, The mass of this water is the volume times the density, and volume is the base times the height. The base, in fact, it comes out to be, if the r radius is given, the base of, it's not pi r square, it's pi r square minus b square. Since this is pi r square, but this is also going to, this b square is all, is also going to take some volume, right? So the base is pi r square and minus this br square. This is the only, if the water does not get into this cube, and of course it doesn't, it's an assumed rigid body, it's not cotton. Pi r square minus b square. It could be, but then it's ice actually. Yeah, it's so volume, that's base times the height. We'll assume the height is h. Volume times density, and density of water is 10 to 10. It's not 10. It's 1. Actually, it's 10 to the power 3 on all the sides, but since it comes out common and we cut the 10 to the power 3 thing, it's just specific gravity into 1, right? Who cares about the units? Anyways. So, yeah, I think, okay. So we know that H is B 0.9. So let's put that here. H is B 0.9. So see, after using distributive property, this and this gets cut, and what remains is this pi r square 0.9b. 0.9 also gets cut. Of course, we did not need this already, I told you. So we need to find b, and b is a cube upon pi r square. Simple. And the a is given to be 4, so it's 64. And we want to find b in centimeters. It does not matter the centimeter. If we take r in centimeters and this in centimeters, it come out in centimeters. So pi r square, right? 64 by 9 pi. Now, how much that is? 9 into 3 is 27. I'll assume it's 28. So 64 by 28 is 32 by 14, which is equal to approximately, let's say, 2.1840. It's nearly 3's up, but it's 2.8, right? It's about approximately 2.28 centimeter. It's the answer. 2.26. This is just an approximation, right? Okay, 64 by 9 pi. By 9. Okay, it's 2.26. Right. What? It's turn to an eraser. What? Uh, yes. The wrong way to do this. I'll talk about two ways. They're wrong. They are right till this thing. Till this thing, they're right. Most of them. Now they say that, you know what h height is? You know what? What is it? They say, see, what they say is the original area volume was A cube. Now we got it as B cube. So the volume that is converted to water is A cube minus B cube. And this thing, the volume that's converted, should be equal to this pi r square minus B square times h. And so they say h is equal to A cube minus B cube upon pi r square minus B square. Right? A cube minus B cube upon pi r square minus B square. Now to get the answer right, see, what they do is they put B into 0.9 is equal to a cube minus b cube or pi r square minus b square. They say this zero point 0.9 is approximately equal to 1. Yeah, that's what they say. The density of ice is approximately equal to the density of water. And of course, if not given, so we'll assume the density of ice to be 1. Wow, such noble actions. So they say it's pi r square b minus bq and a is equal to aq minus bq, one discard. And the answer is of course same. B is equal to a cube upon pi r square. The reason this answer remains same is because they've assumed the density of water is equal to the density of ice. So this volume conservation that they do is right, and then this whole thing is right. But the thing wrong about this, of course, you'll not get a dream that in this particular question we have to take them equal, and of course they're not equal. And the whole thing about volume conservation is wrong, right? Because the volume of ice is different and volume of water is different. You cannot say that these two are equal. In fact, they're not. In fact, this is greater. A cube minus b cube is the volume of ice, and pi r square minus b square h. This is the volume of water. It's less than this. In fact, because it's water, it's denser. The maximum density is at 4 degrees Celsius of water. This is one way but they get wrong. The other way that they get wrong is they do the same thing. They say that it's equal, of course, but they do not have the, I'll say, the dumbness to say that 0 0.9 is equal to 1. Rather, they say, solve it. So R square is also 9. 9 into 9 is 8.1 pi minus BQ 0.9 equal to AQ, which is 64 minus BQ. And this is solve it. It's not our concern. Though we are taking our time, but it's not our concern to solve it and solve it. And when the students will solve it, they'll get B is equal to 2.48, which is wrong. Oh, I think I've no, I think it's 2.48. Assume it's 2.4, but it's still wrong by 0.2 centimeters. And it's a lot. So this is the question basically. Thank you.